All right, let's talk about one of the most famous charts in science, the periodic table. Now, I want you to just forget about that intimidating grid of boxes you had to memorize in school. Seriously, think of it instead as a map, a perfectly logical, incredibly useful map to, well, literally everything in the universe.
I mean, think about it. How can something like gold, this shiny, heavy metal you can bend, and something like helium, a totally invisible gas, even belong on the same chart? What are the fundamental rules that cause these wild differences? Well, that's the big mystery we're going to unravel today.
So, here's the game plan. First, we're going to break our map down into 3 big regions, kind of like continents. Then, we'll zoom in on the great divide between metals and nonmetals. After that, we'll visit a couple of really interesting neighborhoods on the table. And finally, we'll pull back the curtain and reveal the one secret rule that makes the whole thing work.
Okay, first things first. Let's get the lay of the land. You see, just like a world map has continents, the periodic table has these 3 huge, broad classes that categorize pretty much every single element.
The biggest continent by far is the metals. I mean, they take up almost 3/4 of the whole chart. These are the elements you probably think of first: iron, copper, gold. And they all share a few key properties. They're shiny, you can hammer them into sheets, that's what malleable means, you can pull them into wires, which is ductile, and they are fantastic at conducting heat and electricity.
Now, over on the other side of the map, tucked away in that upper right corner, you've got the nonmetals. And really, they're the total opposites of metals. If you find a solid nonmetal, it's probably brittle. It'll shatter if you hit it. They are awful conductors, which is why we use them as insulators. And they're a pretty diverse bunch. Some are solids, some are liquids, and a whole bunch are gases.
So what about the border between these 2 massive regions? Aha, that's where things get interesting. That's where we find the metalloids. They live right on this zigzaggy stair-step line that divides the metals and nonmetals, and they have this really fascinating mix of properties. A metalloid might be shiny like a metal, but brittle like a nonmetal. They're basically the hybrids of the elemental world.
Okay, so this split between metals and nonmetals, it's way more than just about being shiny or brittle. It's a deep, fundamental conflict that is behind, well, almost all of chemistry. It really boils down to this one simple idea. You can almost think of it as a personality trait. Metals are givers. They are always looking for a chance to get rid of their extra electrons. Metals, on the other hand, are takers. They are desperate to grab electrons from anyone they can. This one single difference, wanting to give versus wanting to take, is the root cause of everything else.
And you can see how that one core difference explains this whole chart. Take a look at conductivity. Why are metals good conductors? Because they're happy to let their electrons go. Why are nonmetals insulators? Because they hold on to their electrons for dear life. Or look at how they form ions. Metals lose negative electrons, so they become positive. Nonmetals gain those negative electrons, so they become negative. Every single property you see here traces right back to that one behavior.
All right, to really see this in action, let's take a little field trip. We're going to visit 2 very different neighborhoods on the non-metal side of the map. The wild thing is, they live right next door to each other, but they could not be more different.
First up, let's meet Group 17, the halogens. This family, we're talking fluorine, chlorine, these guys are some of the most aggressive, most reactive elements on the entire table. They are the textbook definition of electron takers.
So why are they so pushy? It's all about the numbers. See, a full, happy, stable outer shell of electrons is 8. Halogens have 7. They are so close, it makes them absolutely desperate to snatch just one more electron to complete the set. And that's why they react so, let's say, energetically with elements from the far left side of the table, like the alkali metals, who are just as desperate to get rid of one electron. It's a perfect, often explosive match.
Now let's just take one step to the right on our map, to Group 18. Meet the noble gases. These are the halogens' next-door neighbors, but their claim to fame is being the total opposite. They are famous for being almost completely unreactive. They're the loners of the periodic table.
And why are they so aloof? Well, it's because they've already got it made. They have what the halogens want so badly, that perfect, full outer shell of 8 valence electrons.
8 is the magic number for chemical stability. They are perfectly happy, perfectly content. They don't need to gain electrons, they don't need to lose electrons, so they just float on by, ignoring pretty much everyone.
Okay, let's leave the drama of the nonmetals behind and journey into the huge central block of our map, the transition metals. This is home to some really familiar faces, right? Iron, copper, silver, gold, nickel, they all live here.
So these are kind of our classic metals. They're shiny, they're great conductors, super malleable, but they have a really cool trick up their sleeve. See, most metals only lose electrons from their outermost shell, but transition metals, they can actually lose electrons from 2 different shells. This special ability lets them form ions with different charges. It's why you can have both iron 2 and iron 3. And it's also the secret behind the absolutely beautiful, vividly colored compounds they can form.
So, we've toured the map. We've met the super reactive families and the super chill ones. We've seen the versatile metals in the middle. We know it all has something to do with giving and taking electrons. But what is the one single ultimate organizing principle that explains it all?
It's really this simple. An element's entire personality, whether it's shiny, how it reacts, if it's a solid or a gas, absolutely everything is decided by how its electrons are arranged. Specifically, it's about those outermost electrons, the ones we call valence electrons. They're the real currency of the chemical world.
So how does this explain something like conductivity? Well, for metals, this quote nails it. The electrons delocalize. That's a fancy word, but all it means is they aren't tied to any one atom. Instead, they form this free-floating sea of electrons that flows around all the metal atoms. It's this mobile sea that lets electricity pass through so easily.
And here's the other side of that coin. Why are nonmetals insulators? For the exact opposite reason. Their electrons are held on tight. As the source says, they just don't have that high degree of movement. There's no free-flowing sea of electrons, so there's no conductivity. It really is that straightforward.
So, the next time you glance at a periodic table, don't see an intimidating chart you have to memorize. See it for what it really is, a cheat sheet, a tool for making predictions. Because if you know where an element lives on this map, you know how its electrons behave. And if you know that, well, in a way, you can predict its future.